Welcome back to the show. Today we're doing a deep dive on something pretty wild.
Oh, yeah.
Deep water pressure systems for clean energy.
Mm.
Yeah, you might be thinking, water pressure? Really? But
Yeah.
how's that? It's way cooler than it sounds, trust me.
Okay.
Basically, we're talking about like all that incredible pressure at the bottom of the ocean
Right.
or lakes, reservoirs, you name it.
Yeah.
Using that to actually generate power.
So like an underwater power plant.
Kind of, but way more awesome, you'll see.
I'm intrigued.
We're going to get into how much power these things could make.
Oh, okay.
Like potentially powering entire regions, maybe even some crazy connection to quantum computing. Who knows?
That's a lot to untack.
It is. But first I got to ask, what even made you think of this? I mean, water pressure is an energy source. It's not exactly something you hear every day.
Well, to be honest, it kind of started with a what if question.
Oh.
Yeah, like what if we could flip the script on how we think about pressure? Instead of it being a force working against us, could we make it work for us?
So turn that pressure into like potential energy.
Exactly. And the more I looked into it, the more I realized the potential is enormous. We're talking about a whole new paradigm for clean energy.
That's what's got me so excited about this, the sheer scale of it. From the stuff you sent me, we're not just talking about replacing a little bit of our energy needs here.
Not even close. We're talking about exceeding what we get from oil by a lot, potentially.
Whoa. Okay, hold on. Let's not get ahead of ourselves. Before we start celebrating an oil-free future, we got to break down how these deep water pressure systems actually work. What's going on down there in the depths? Give me the nuts and bolts.
All right, picture this. You've got a system of chambers and valves all built super tough to withstand incredible pressure.
Okay, so far so good.
Now, there's an intake valve at a depth where the pressure is already pretty serious. This valve lets water flow into a chamber.
All right, so the water's coming in. What then?
Inside that chamber, there's a specially designed turbine.
Got it. So is it like the water pressure itself pushing the turbine?
Exactly. No dams or rivers involved like with traditional hydropower. Just pure water pressure driving that turbine, making it spin.
Okay, so the pressure spins the turbine. Then what?
Well, that spinning, that rotation is key. It converts the water's movement, its kinetic energy, into mechanical energy. That's what we can use.
To generate electricity.
You got it. That mechanical energy powers a generator, and boom, we've got electricity.
I'm with you so far. So the water comes in, pushes the turbine, makes electricity, but then what happens to the water? Does it just flow back out into the lake or ocean?
Nope, there's more. Instead of releasing it right away, we direct that water into another chamber.
Another one.
Yep, and this one's designed to use gravity to compress the water even more. So we're basically amplifying the pressure, squeezing even more energy out.
That's pretty clever. But at some point, the water's got to go somewhere, right?
Of course. Eventually, we release it back into the lake or ocean.
Okay.
But it's done gradually in a controlled way to minimize energy loss.
So it goes from high pressure to a chamber with slightly lower pressure.
Yep. Smoothes out the flow, prevents turbulence. Then finally, it's expelled through a one-way valve. Keeps the whole system flowing.
I gotta say, this is way more intricate than I imagined.
It's a beautiful dance between natural forces and clever engineering, wouldn't you say?
Totally.
Yeah.
And we can make it even more efficient with the right design, right?
Absolutely. Think variable pitch turbines that adjust to changes in water flow, advanced materials that can handle the extreme pressure, stuff like that. The future of material science is going to play a huge role here.
Speaking of materials, it's one thing that really jumped out at me from your research. I mean, we're talking about incredible pressure, constant submersion. What kind of materials can even handle that?
We're talking about the toughest stuff out there. Titanium alloys, for example, are known for their strength and resistance to corrosion.
Yeah, I've heard of those. Anything else?
We're also looking at advanced composites, materials engineered to have specific properties to survive these brutal conditions. Durability is key here. We need these systems to run for decades, with minimal maintenance.
Which makes sense, but how do you even maintain something that's hundreds, maybe thousands of meters underwater? You can't just send a diver down there, right?
Exactly. Traditional methods are out the window. We're talking remotely operated vehicles, ROVs, autonomous underwater vehicles, AUVs, little robot buddies equipped with sensors, tools, the works. They're the maintenance crew for the deep.
So underwater robots keeping our clean energy system humming along.
Pretty cool, huh? And with sensors sending data back in real time, we can monitor the system's health constantly.
Pressure, flow rate, any potential problems.
Yep, all of that. Minimizing downtime, maximizing efficiency. It's like having a finger on the pulse of the system, even though it's way down there in the dark.
Now, before we get too deep into the potential energy output of these things,
Okay.
there's something else I wanted to touch on from your research.
What's that?
That letter advocating for these deep water systems that was sent to, of all people, former President Donald Trump.
Oh, yeah, that one.
It really highlighted the sheer audacity of this tech. Like, it could be a game changer, not just for energy, but for everything.
Yeah, that letter went beyond just the technical stuff. It was about the geopolitical implications, too.
It was like deep water systems
Yeah.
as a way to become energy independent, right? Superior to oil drilling. A pretty bold claim.
Definitely bold. But that's what made it so intriguing. It got me thinking about the big picture. And the letter specifically mentioned using the Great Lakes for these systems. Do you think that's even a viable option?
Yeah, I was wondering that too. Are the Great Lakes even deep enough for this to work?
Well, it depends. We got to look at the depth profiles of each lake, right?
Okay, so some are deeper than others.
Exactly. Lake Superior, for example, has areas over 300 meters deep. That's perfect for this. But others, like Lake Erie, are much shallower. Wouldn't be as effective.
So location matters. It's not just any body of water that can support this type of system. But I'm guessing the author of that letter had a reason for focusing on the Great Lakes, right? What was their logic?
Well, according to the letter, the Great Lakes alone could generate enough power to rival a significant portion of the energy the U.S. gets from oil.
Hold on. So just the Great Lakes could replace a big chunk of our oil consumption.
That's the claim, and that's what we need to investigate. Is that even remotely realistic, or is it just wishful thinking? To find out, we got to crunch some numbers.
All right, let's do it. Let's see how much energy we're really talking about here.
All right, so let's talk numbers. How much juice can these deep water pressure systems actually make?
That's the million-dollar question. Or more like the multi-billion-dollar question, maybe.
Huh, right. But keep in mind, we're not talking about turning every inch of the Great Lakes into a power plant. You know, we got to
No.
be realistic.
Yeah, got to think about stuff like the lake bed, shipping routes, existing infrastructure. Oh, and, not destroying the environment.
All those things, absolutely. It's about finding those sweet spots where the technology makes sense.
So let's say, hypothetically, we could use, 30% of the deep water areas?
Let's go with that for now, 30%.
Okay, 30% it is. So based on that, how much energy are we talking? Give me the good stuff.
All right, buckle up. Our calculations show that one system, deployed at a depth of 300 meters, could generate roughly 7.05 megawatts of power.
Okay, 7.05 megawatts. And Lake Superior, like we said, is huge, right? So how many of these systems could we fit in there?
Well, assuming that about 25% of Lake Superior's surface area is suitable and applying that 30% usability factor,
Right.
we're looking at over 6,000 square kilometers we could potentially work with.
6,000 square kilometers. That's bigger than some countries. How many systems could we fit in an area that big?
Let's say we space them out a bit, maybe one per square kilometer to avoid any interference and keep things running smoothly. We're talking over 6,000 systems in Lake Superior alone.
Whoa, okay. And each one's pushing out over 7 megawatts. So that's, hold on, let me do some quick math here. Over 43 gigawatts, am I right? That's got to be enough to power millions of homes.
You got it. And that's just Lake Superior. We haven't even factored in the other Great Lakes yet.
Right. So we add Lake Michigan, which also has some pretty deep spots. And we're doubling that number?
Not quite doubling, but close. Lake Michigan could probably contribute another 14 gigawatts or so.
So we're looking at like 57 gigawatts of clean energy just from 2 lakes. That's insane. How many power plants would that replace?
Dozens, easily. But without the pollution, the emissions, all the nasty stuff that comes with traditional power plants.
Okay, but hold on a sec. Remember that letter we talked about? The one claiming that this could replace a big chunk of the energy we get from oil.
I remember. A bold claim, for sure.
Right. So is that even realistic? Or was the author just trying to get people's attention?
Well, the numbers do seem to add up. The U.S. uses about 2,000 terawatt hours of energy from oil every year. Our calculations suggest that the Great Lakes could potentially produce over 600 terawatt hours per year.
So almost a third of our oil consumption, just from the Great Lakes.
That's what the numbers are telling us. And remember, that's just 2 lakes. Think about scaling this up. Oceans, seas, reservoirs all over the world. The potential is mind-blowing.
It really is. It's like we've had this massive source of clean energy right under our noses this whole time.
We just needed to figure out how to tap into it, and that's where the real innovation comes in.
Right, right. But let's shift gears for a moment and go back to that letter to President Trump. Remember, it talked about energy dominance. What do they mean by that exactly?
The author was basically arguing that deep water pressure systems could free the U.S. from its reliance on foreign oil.
Oh, I see.
It painted a picture of the U.S. becoming a major energy exporter, a global leader in this new technology, shaking up the whole geopolitical landscape.
Wow. It sounds almost too good to be true.
It does, doesn't it? But that's what makes it so exciting. It forces us to ask, what if? What if we could actually break free from oil? What would that mean for everything? For our economy, for the environment, for global politics?
It's like a glimpse into a whole different future.
Exactly. And that's why I find this so fascinating. It's not just about the technology itself. It's about the potential to reshape the world as we know it.
I'm totally with you. This is way more than just building some underwater power plants.
It's about redefining our relationship with energy. And that's a conversation worth having.
Absolutely. Okay, so we've talked about the amazing potential, the mind-boggling numbers, but let's get real for a second. Every technology has its challenges, right? What are we up against here?
Of course, there's no such thing as a free lunch, especially when it comes to something this ambitious.
So what are the hurdles? What do we need to figure out?
Well, we've already touched on some of them. Material science, for one.
Yeah.
We need stuff that can withstand the crushing pressure and the corrosive environment down there.
All right, got to make sure these systems can actually survive in the deep.
Exactly. Then there's the whole maintenance thing. We need those robots to be reliable, efficient, and adaptable.
Makes sense. What about environmental impacts? We don't want to solve one problem just to create a bunch of new ones.
Of course not. Minimizing the impact on marine life is a top priority. We need to do our homework and make sure we're not disrupting ecosystems or creating unintended consequences.
And then there's the question of scale. How do we actually build and deploy these systems on a massive scale? That's going to take some serious resources and coordination.
It will. And then there's the issue of grid integration. How do we take all this clean energy and plug it into our existing power grids? Our current infrastructure isn't really built for this kind of thing.
So it's not just about building the systems, it's about rethinking our entire energy infrastructure.
Exactly. It's a huge challenge, but it's also a huge opportunity. We're talking about a paradigm shift in how we think about energy.
And I'm sure our listeners are eager to hear about how we're going to tackle these challenges and what the next steps are in making this incredible technology a reality.
Let's dive into that next. So we've got these challenges, but the cool thing is, people are already working on solutions.
Oh, yeah. Like, what? Give me some help here.
Well, take biofouling, for example. We were talking about those special coatings, remember?
The barnacle-proof stuff.
Exactly. That's a big area of research right now.
So how do those coatings work?
Well, there are a few approaches. Some coatings create a super slippery surface, so it's hard for anything to latch on.
Clever.
Others use biocides, basically substances that deter organisms from settling down in the first place.
So, like, keeping the critters at bay.
Exactly. And, I bet nanotechnology will play a big role in these coatings, too.
Oh, yeah. How so?
Well, nanomaterials have these unique properties, like you can make them super slippery or water repellent, stuff that's really tough to do with normal materials.
So we're talking, like, next-level coatings here, not just slapping on some paint.
Right. It's about engineering materials at the molecular level, making them durable, effective, and most importantly, eco-friendly.
Right, we don't want to solve one problem and create another.
Exactly. Okay, now what about that other big challenge, grid integration?
Yeah, how do we handle all that extra power coming from these systems, especially if they're making more than we need at times?
Well, that's where energy storage comes in. Think of it like a giant battery for the grid.
Oh, I like that analogy.
We can store that excess energy when we have it, say, when the sun's blazing or the wind's blowing strong, and then release it later when demand is high.
Smart. So instead of wasting all that clean energy, we're saving it for a rainy day, or I guess a not-so-windy day.
Exactly. And there are other energy storage options, too, like pumped hydro.
Pumped hydro? What's that?
Basically, you use excess energy to pump water uphill to a reservoir. Then, when you need power, you release the water downhill, spinning turbines to generate electricity.
So we're talking about a totally different way of thinking about energy, not just relying on big power plants anymore.
Exactly. It's about creating a more distributed, more flexible energy system, one that can handle the ebb and flow of renewable sources like deep water pressure.
And you know what? This whole conversation has really got me thinking. This tech could have implications far beyond just generating power, right?
Absolutely. Think about it. If we can tap into this vast clean energy source, how would that change things? Our economy, the environment, national security, even our everyday lives.
Where it's like a whole new world of possibilities opens up.
It really is. It makes you realize just how interconnected everything is. Energy touches every aspect of our lives.
And this deep water pressure idea, it's like a catalyst for change.
I think so. It forces us to rethink our assumptions, to explore new ways of doing things.
And that's what I love about these deep dives. They make you step back and see the bigger picture.
Me too. It's a reminder that there are always new frontiers to explore, new solutions waiting to be discovered. We just got to keep asking questions, keep pushing the boundaries.
Well said. So to all our listeners out there, keep exploring, keep questioning, and keep diving deep. Until next time.